This is the analysis and redesign of a handheld spreader by Team 15.
To use a handheld manual spreader, the user fills the hopper with material to spread across a lawn or a garden. Then the user spins the handle wheel to turn the gears attached to the spreading wheel. These spreaders are easy to use and robust, plus they are very portable. This is an exploded view of all the components of the handheld spreader.
The spreader's primary customer is a homeowner who will utilize the product for personal usages. It will have minimal usage and is expected to only be used once a week at most, so there will be long periods of disuse. The secondary customer are service providers who will utilize the product for business or commercial usages, so it will be used a lot and needs to be durable to withstand this constant usage.
For the functional analysis, the task function of our product is distribute product. The basic functions that achieve this task function are project product, disperse product, and contain product. To assure dependability, the product will prevent clogs and leakage. To assure convenience, the product will control flow. To enhance product, the product will stop flow, and to have multi-material compatibility. For please senses, the product is lightweight, balanced, and comfortable.
Here we present the two fishbone diagrams with the proposed assembly sequences. Assembly sequence 1 is a bottom-up approach, while assembly sequence 2 is a top-down approach. Assembly sequence 1 starts with the installation of 5 individual components to the base, followed by the installation of the handle subassembly, handle lower subassembly, and the hopper component to give us the first assembly sequence. Assembly sequence 2 starts with the hopper, followed by the installation of 3 separate subassemblies we are calling the handle lower subassembly, base subassembly, and the handle subassembly. Assembly sequence 1, the bottom-up assembly, was determined to be the preferred method of assembly, with sequence 1 outweighing sequence 2 in nearly all key criterion.
Now the functional component mapping matrix, which identifies how each element of our handheld seed spreader contributes to the system's overall functions. The spreader is made up of several components that work together to perform key tasks, and this matrix highlights those relationships. In particular, it shows which functions are critically dependent on specific parts. For example, project product's primary function relies heavily on the spreading wheel. Overall, this matrix illustrates how all components interact to deliver the spreader's intended performance.
The bill of material is composed of 13 unique parts, with one standard component being screws. The majority of the components are made from polypropylene and are injection molded. The 3 gears are manufactured from 1117 steel and our CNC machine from bar stock. The material, assembly, and tool costs for each components are shown in the table, and the total cost of manufacturing is $24.39 compared to products on the market, which is $22, which is an 11% increase to competitor products. The DfM DFA quad chart maps the product's functional importance versus manufacturing cost. With most of our parts with high functional importance and low manufacturing cost, this ensures that the product will be best value for the customer.
This slide shows how we use a functional differentiation table to guide the design of our handheld seed spreader. We focus on keeping core functions like spread product, project product, and the rest shown on the table the same across all models, while customizing features shown as feed control, contain product, and handle ergonomics for different users. This approach allowed us to balance shared efficiency with tailored usability, ensuring each design feels purposely built without adding unnecessary complexity.
3 components are different in the spreader between the 2 customer groups. These components are the hopper body, feed control, and the handle cap. The hopper body will be larger for the secondary customer group. The feed control will either be basic or advanced, providing more slot opening options for the feeder. And the handle cap will either be simple or have an ergonomic design, which also allows the user to provide more force when turning. Here we can see the design changes between those 3 components. The hopper body is larger for the secondary customer group, allowing the user to spread more product and reach a larger area. The feeder control either has 1 opening for simple usage or 3 openings to assist with the flow of products and adjust to the product size, whether it be fertilizer, seed, salt, etc. The handle cap either is simple, just going on the end of the handle present, or as there is an ergonomic handle cap, which will benefit those who are continuously using the spreader. Here we can see the exploded view of the product for the secondary customer group. You can see that the hopper body, feed control, and handle cap are all highlighted in red, showing where the differentiation is between the primary and secondary customer groups.
The original assembly sequence yields what we deem to be the most efficient assembly sequence when also factoring additional variants. Delaying assembly of the variant parts like the handle cap, feed control, and hopper body yield the most efficient use of time and cost, all while mitigating overall assembly complexity.
Here we can see the design efficiency analysis for design for manual assembly both before and after component modifications. Before modifications, there were a total of 20 parts and a design efficiency of 29.7%. After modifications, there are 13 parts and a design efficiency of 68.33%, which is almost 2.5 times better. Shown here are the modifications to the bin and the base. For the bin, screw bosses were removed in place of snap features. These snap features were placed in such a way that the bin cannot be assembled in the wrong orientation, creating a poka-yoke design. For the base, the handle support lower was added to the body to remove part counts, and mating snap features were created to interface with the bin. One wall was extended to ensure a snap feature could be incorporated, which increased the part symmetry.
The chart on the left shows the time for the original assembly that contained 12 components and one screw. The time for the original assembly was 10.538 seconds. By making the modifications and removing 3 components, we were able to reduce this time to 9.362 seconds, which gives a total reduction of 1.176 seconds. The modifications made are shown here. The first modification was to combine the handle cap and handle body into one single part. The other modification was to combine the handle inner and outer into one component that contains locking tabs, so that this part would be easier to assemble.
The overall diameter of 42 millimeters and the inner bore diameter of 8 millimeters support the product function of a supporting structure, providing strength and stability to the seed spreader handle. The redesigned handle inner and outer, now a single part with snap clips, easily connects to the body and rotates freely around the hopper and base. This simpler assembly reduces part count and improves installation efficiency. The overall diameter of 110 millimeters and the handle height of 26 millimeters are the main dimensions that support the product function of control flow. These dimensions allow the user to spin the handle body with enough leverage and force to confidently control the amount of product being released at one time. The new design consolidates the 3 original separate parts into one. This ensures a more robust design and reduces overall part count. For each redesigned part, we have selected 2 candidate manufacturing processes amongst machining, injection molding, die casting, and sheet metalworking. Selections were made based on 7 different process capabilities, including shape, mass, section thickness, tolerance, surface roughness, and economic batch size. For the handle body and handle cap, the 2 candidate processes are machining and injection molding. For the handle inner and outer, the candidate processes are machining and die casting. For the handle cap and body, we are recommending injection molding as the manufacturing process. This is due to the economic batch size limitation and the choice of thermoplastic as the material. For the handle inner and outer, we are recommending machining as the manufacturing process. Based on material selection of aluminum and the use of strategic tooling choices, we believe we can overcome the economic batch size limitation. This will ensure a higher quality product that will be less prone to failure.
DfM was performed on the handle cap body analyzing injection molding using SOLIDWORKS CFM Pro. Improvements were made using the DFIM rules, improving cost by $0.053, improving cooling time by 7.2 seconds, and decreasing part volume by 48% compared to the original design.
Now highlighting our design for manufacturing improvement. Originally our handle inner and outer were 2 injection molded pieces, now become 1 machine part. To meet new machining requirements, we're able to develop this premium and robust part. While the transition increased unit cost from 10 cents to 68 cents or 58 cents when directly quoted from the hub, the trade-off delivers significant benefits. Tighter tolerances, improved durability, and more premium feel, while most importantly getting rid of legacy issues.
The proposed product service system is a one-stop shop app for the product. In this simple app, the user can access training guides, weather and climate information, report issues, and sign up for subscription services to provide the most optimal seeds or salts needed by the user.
Conclusion. Our handheld seed spreader was designed to be lightweight, ergonomic, and cost-effective while still delivering reliable seed distribution. By applying DFA and DFM principles, we simplified the design, reduced the part count, and made the product easier to assemble while being more robust. While stronger materials improve durability, some machine components increase costs compared to an injection molded approach. If we were to start over, we'd focus on developing a better mechanism for releasing materials from the hopper to the spreading wheel. Thank you for your time.